Confidence intervals are an often misunderstood concept in statistics. If we start with the overall picture of statistics, that might help us understand the purpose of confidence intervals and then how we might be able to interpret them. The whole purpose of statistics is to help us understand characteristics about a population. Populations are often very large, and it would be too time-consuming or expensive or just impossible to look at every subject or object in the population. If we could calculate what are called parameters. These are numeric values computed from the entire population. For example, the population mean mu represents the mean of all of the subjects in the population. Now, we almost never get to know what these parameters are exactly. And as I mentioned before, the population is too hard to look at everyone. And so what we'll do is take a representative subset from that population called a sample. And the sample is easy to get our arms around. Maybe we can't look at everyone, but maybe we can look at 30 people or 100 people. So the sample provides us with numeric quantities that are called statistics. For example, X bar might represent the sample mean. This is the process by which we get to know some properties of the population. X bar represents our best guess at what the population mean is. Now, a lot of that, of course, depends on how the sample has been taken and if we've been cautious and careful that it's representative of the population. But ultimately, our statistics represent a good, educated guess about population parameters. This is the process of statistical inference. Now, a couple of important notes about this process. First is that the sample statistics are not going to be equal exactly to the population parameters. In fact, there's probability 0 that X bar is exactly equal to mu. But if we've been careful in selecting our sample, hopefully those statistics are close. So rather than just report the statistics, we'll report a little interval around the statistic. So for example, I'll report X bar plus or minus some margin of error. And that margin of error is meant to give me a feel for the uncertainty in my statistic. And while X bar might not exactly be equal to mu, hopefully my interval around X bar captures the true parameter from the population. This point estimate X bar plus or minus a margin of error is what we refer to as a confidence interval. You'll often hear things about a 95% confidence interval or 90% confidence interval. How do you interpret a 95% confidence interval? In this video, we're going to talk about a web app that allows us to visualize this process in a simulation for certain population parameters and how those intervals are constructed so that we can understand what it means to be 95% confident that our interval contains the true parameter. This web app allows us to visualize confidence intervals for populations with specific features. I can modify the input parameters to specify the population having a specific mean and standard deviation, indicate the sample size that I'll be drawing from that population, and what level of confidence I'm interested in. For example, if I were to draw a sample from a population with mean 20 and standard deviation 8, and perhaps I want to take samples of size 20 and construct a 95% confidence interval. When I click submit, that generates my 20 observations from a population with these characteristics, and it plots the lower bound and upper bound of that confidence interval on this plot. The vertical blue line corresponds to the true population mean, which is at 20, and you can see that this interval captures the true mean of interest. I can simulate by specifying the number of simulations that I'd like. So with the interval I already have, I'll ask for 99 more, and it will quickly generate those samples and construct their confidence intervals. And it marks with red the intervals that don't contain the true population mean of 20. In this simulation of 100 samples, there were 3 confidence intervals that did not capture the true parameter of interest. At the top of this tool, it keeps track of the intervals that have been generated, tells me how many of them did not contain mu, and then calculates a percentage of the intervals that captured the true parameter of interest. In the top right, we have a plot that shows me over the samples that have been taken what that coverage probability is, and we will expect that it converges to the 95% confidence we specified for these intervals. Now, this helps us understand what we mean when we say we're 95% confident that this interval captures the true parameter of interest. There's a probability contained in that statement, but the probability pertains to the intervals that are constructed. 95% of the intervals we construct in this way will contain the true parameter of interest. When we say we're 95% confident that the interval contains the true parameter, in a way we're playing the odds, saying, yeah, it's possible that this interval doesn't contain the true parameter of interest, and in fact, we really don't know if the interval we observe is a red interval or a black interval, but we are playing the odds that we are more likely to get one of the black intervals than we are to get one of the red intervals. So, samples constructed in this method 95% of the time will capture the true parameter of interest. Notice that that probability statement is about the interval, not about the parameter. The parameter, from a frequentist perspective, is fixed. It doesn't move around, it doesn't have an associated probability. What moves around are the random samples that we take and ultimately the confidence intervals that are computed from those samples. So each one of these confidence intervals represents a sample with a computed mean and the respective margin of error that got us to a lower bound and an upper bound, as we saw on the first slide. Hopefully this gives you a sense for what it means to have 95% confidence that our interval contains the true parameter of interest.